Hey guys, I'm gonna try to make this short and sweet today. Trying to get this in real quick this morning before I have kids in here. So I'm gonna try to record in one try without having to go back and re-record it. So bear with me. Today we're gonna talk about velocity time graphs. So we've been talking about position time graphs, which tell you can calculate the instantaneous velocity using those. If you have a linear graph or a position time graph, you can find the average velocity. Velocity time graphs, you're just switching position for velocity, and these are going to give you even more useful information. So in any velocity time graph, velocity is going to be your independent variable now, and then time is still your dependent variable. So again, you're just reading values off your graph. You're going to find the slope of your graph, and then we're going to add on finding the area underneath the graph. So you have two situations here. Actually, this is one situation, two different graphs. So the graph on the left is representing a student walking to school with a constant velocity of 1.33 meters per second south. He travels 80 meters, so his position changes from 0 to 80 and his time over the time frame of 60 seconds. On the right, you have a velocity time graph, and this is representing the same information. So you have a straight line all the way across. So now we have a slope of 0, which means that his acceleration was 0. So he has a constant velocity. So if you have a straight line on a velocity time graph that is above 0, it means that you are moving with a constant velocity. You're not speeding up or slowing down. So similarities between these, the time scale is going to be the same. Your units are similar. You're still using seconds and meters. The positive direction is still going to be the same. Some differences would be that the units on your vertical axis are going to be meters per second instead of meters. Your position time graph is going to have a positive slope if it's moving, and then your velocity time graph would have a 0 slope for the same information. And the position and the velocity will be obviously labeled differently. So we talked last class, the example was talking about this kid that's walking to school. He travels 80 meters in 60 seconds. So his instantaneous velocity there was 1.33 meters per second south. So if you look at that same information on a velocity time graph, you're going to get a flat line. Okay, so you can tell that he's going 1.33 meters per second south by your y-axis, and then from the time of 0 to 60 seconds, we're moving at a constant pace. Okay, so again, this is just going through here like why you would come up with the units you do. So if you were calculating the slope of this and you maybe just needed to see it, we know that a flat line would have a 0 slope, but if you're looking at it with the units, technically you're having final velocity minus the initial velocity over the final time minus the initial time. So what you're getting there are these units. You're going to have meters per second, which is velocity, over seconds. So when you break that down, it's going to be meters per second, or meters per second squared, which we already know is the unit for acceleration. So you can use velocity time graphs to calculate acceleration. So for these, if you find the area beneath the graph, this is going to tell you the displacement. Okay, so we know that area is length times width. So you're going to use the same information from your graph. So if you look here, this has the area. We have the length is 60 seconds and the width was 1.33 meters per second, which matches up here. So length would be 60, okay, 60 across, and then the width is the height basically. So you'd go up to 1.33. So that's what we have here. We have length times width gives me 80 meters because seconds would cancel. We have 80 meters south. So this is our displacement. So since it gives us a direction, it's not just a distance, it would be your displacement. And it's going to have the unit and the direction along with that. So summary for just a linear straight across velocity time graph, you can find the velocity, you can find the slope, which gives you the acceleration, and then you can find the area underneath the graph, which is going to tell you the displacement of that object. So when we're looking at graphs that are showing acceleration, these are going to be a little more interesting. They're slightly more work to calculate here. So these two things here, we've got position time graph on the left. Again, since it's accelerating, you have a curved line. It's an exponential graph. So you can see where they drew their tangent lines, and they would have been calculating, like using their final position in time minus the initial position in time to calculate the instantaneous velocity at this point. On this side, we have velocity versus time graph. It's showing the same information, okay? So your velocity over time is increasing, which is showing exactly the same thing on the left. It's just going to be represented slightly differently because obviously you have different labels, different variables on your axes. So here you can see that the velocity obviously is increasing as you move along the time. So both of those graphs are showing the plane taking off from a runway. And we knew that we could find the instantaneous velocity of the position time graph by using the slope of a tangent line. So if we are going to find the position of a plane after 5 seconds using the graphs we were just looking at, if you use the position time graph and you just read the graph, it's going to tell you it's about 65 meters west. So if you flip back here, so after 5 seconds, yeah, we're about 65 meters west. That's not very exact though. So a velocity time graph would do a better job of showing the position after 5 seconds. So to do that, that's what this highlighted portion is. We have to find the displacement, which would be the area under the line. So at 5 seconds, we're going to go up to our line. So our velocity, our velocity is 25 meters per second west at this point at 5 seconds. And then we're going to find the area down here. So we have to use our area of a triangle formula, which is this. Okay, so we have 1/2 base times height. Okay, so the base was the 5 seconds going across your x-axis, and then the height going up was 25 meters per second, which gives you an exact displacement of 62.5 meters west. So both of these graphs are going to give you the same type of information, but depending on what you're looking for, some are better at describing things than others. So if you're looking for the position of an object after a certain time, you want to use the velocity time graph and calculate the area under the graph because it gives you a more exact or a more precise measurement. So if you're going to find the instantaneous velocity at a certain time, here you'd want to use your position time graph because this is going to give you an exact answer. So you're going to find the slope. Oh, sorry, I'm getting these mixed up. So with your instantaneous velocity, you can use your position time graph and you're going to find the slope of your tangent line. So again, if we flip back all the way back here, they drew their tangent line. They're using the points at 150 meters per second, meters, and then 8 seconds. And then down here, they're going to use their initial position of 90 and time of 6 seconds. And you can plug that in, final position minus initial position over final time minus initial time. It's going to give you a velocity of 30 meters per second west. If you use the velocity time graph, you can read it straight from the graph because it is here. So at, where were we at, 7 seconds, you can go up and find exactly what the velocity was at that point in time. So 35 meters per second west. So again, it's more accurate, it's more exact to use your velocity time graphs just because you can have slight variations in how your tangent line is drawn. So if you had an angle just a little bit more or less, you could have slightly different points, or if you weren't very exact with your measurements, you could be off just slightly. So velocity time graphs are going to give you a lot of information here. So you can find your position using the area, and then you can find your instantaneous velocity as well. Okay, so for the examples that we've just used, the velocity time graphs have been linear, meaning that the acceleration is constant, meaning it's not changing. But, oops, oh my goodness, where have I gone? Okay, so if you have a linear graph in a straight line, so we have a constant acceleration, we're constantly accelerating here. You want to find the acceleration during this time frame for this object. So we'd have the final velocity minus the initial velocity divided by the final time minus the initial time. So here our final velocity was 40 meters per second, initial was 0, the final time was 8 seconds and the initial time was 0 seconds. So that tells us that our acceleration for this time frame of this object is going to be 5 meters per second squared west. So velocity time graphs can be used to create a position time graph and vice versa. So we're going to analyze a graph here. So if you were to describe this graph using the motion, you want to think about how you would do that. So if you're looking at this, this is in the positive direction. So the velocity is constant here from 0 to 30 seconds. So you are traveling at 20 meters per second east, constant velocity, 0 acceleration because our slope is 0. And then at 30 seconds, your velocity starts to slow down. So from 30 seconds to 60 seconds, you're slowing down. You come to a complete stop, and then you turn around. When you cross your 0 axis, when you cross the x-axis here, that means that you have changed direction. So if they're going east at 20 meters per second, they're slowing down, they stop, they turn around, and they start to speed back up, going in the west direction. Once they hit 20 meters per second west, which is what the negative indicates here because it's opposite of east, now they're going at a constant speed again. Okay, so that's what this is showing. So you end up having a longer time frame where you're walking west than you were walking east. So when we look at this, I'll show you on a position time graph. You end up walking basically a little bit east, and you turn back around and you walk back further west. So you're going to end up going west in this scenario because you're going west from this whole point on. Okay, so if we're looking at the velocity after each object, you can just simply find that on this graph. You can look right at the graph and see where you're at after 30 seconds or 70 seconds or wherever. Just pay attention to the direction. So the bottom half of these numbers on the second row of this table is showing that they're all moving in the west direction, which is true because after you cross the x-axis here, you're turned around and you're moving west. Okay, so what is the acceleration of the object between 0 and 30 seconds? So from 0 to 30 seconds, your acceleration would be 0 because the slope of this line is 0. What's the acceleration between 30 and 90 seconds? So since you are going from a positive down to a lower number or a negative, you want to look at it this way. So your initial velocity is going to be negative 20 meters per second. Oops, sorry, you're going all the way down here. That's what this is. So you're going from the top here where you start to slow down, you've turned around, and now you're speeding back up. So the acceleration in this time frame, you're going to have the final velocity is going to be negative 20 meters per second. So at 90 seconds, you're at negative 20 meters per second. And then your initial velocity here would be 20 meters per second because that's where you're at. For the time, you're going to have 90 seconds minus 30 seconds. So what you should get on top is a negative 40 meters per second and then divided by 60 seconds. So let me put this. Oh, this little thing go back down on the bottom. Okay, so for acceleration, you're going to end up with 0.6 repeating meters per second squared west. Okay, and we know that it's west because this answer is negative. Okay, so when you take a negative 40 and divide it by 60, your answer will be negative 0.6 meters per second squared. And since we know what the initial and final directions were, we can show this as a positive number in the opposite direction. So we can do the same thing again from 90 to 160. So from 90 to 160, you had another flat line, which means no slope and constant velocity. So in a velocity time graph, this indicates movement, you're moving, whereas a position time graph, a flat line indicates that you've stopped, but you do not have any acceleration on these flat points. Okay, so what would be the significance of the point at 60 and 0? So at 60 seconds and the velocity is 0, it means that you have stopped and you're turning around. Like since this goes down and then it crosses the x-axis, that's the point where you're turning around. So determine the position, just like I'll wrap up here, you're going to find the area between the graph and the time axis up to that point. Okay, so you're basically finding the area under the graph to determine the displacement or the position. So it's usually easier to find the areas of different sections of the graph and then add them together afterwards. So for the graph that we've been talking about, we are going to find the areas, and you'll see what I mean here. So we've broken this up into 4 sections because we can very easily calculate the area of a rectangle and then the area of a triangle and add them together. So that's what we are going to do here. So for this box, for the A1 box, it is just length times width. So we have 30 seconds times 20 meters per second. So the area of this spot here is going to tell us that the displacement is going to be 600 meters east. Okay, so his new position, he's moved 600 meters east in this time frame. For A2, we're going to have 1/2 base times height. So the base here, we're going from 30 to 60 seconds. So the base would be 30 seconds long, and the height is still going to be 20 meters per second. So the second area is 300 meters east. Okay, so eventually we'll be adding this one, the 600 to the 300. So that tells us that they've moved 900 meters in the east direction. And then we hit A3, area 3. So this is beneath the x-axis. So you do need to make sure that you're showing that with the height measurement. So again, it's a triangle. So we have 1/2 times the base, which is 30 seconds because it's going from 60 to 90, times the height, which now is -20 because we are 20 down. So it's going to give us an area of -300 meters east. And then we do the same for the last area here. So the last area is a little bit larger. So we're going to have a length of 70 seconds because we're going from 90 seconds to 160 seconds. And then the height is going to be -20 as well, or the width, I guess. So it's going to be -20. So when you do your math, you should get -1,400 meters east. So when we start looking at this and we're adding them up, so from 30 seconds to 60 seconds, that's where we were in the positive direction here. We're in the east direction from 30 to 60 seconds. We have a total displacement of 900 meters east. So then when we look for the rest of the graph, the bottom half, we have 90 seconds to 160 seconds. You would have 600 meters in the first part of that where the triangle was, and then you're adding the -1,400 meters to that to get 800 meters west. Okay, so what this is showing you is that you have basically gone further in the direction west than you did east. You have crossed over your starting point. So if we look at that, you can see that obviously this yellow square is much larger than the blue one. You could say that A2 and A3 are probably exactly the same. Obviously A1 and A4 are not. So what that's showing is that when you crossed over, you stopped and you turned back around, you went back beyond your starting point in the opposite direction. So you ran east and then you turned back around, you ran west, but you went back further than you started. Okay. So to graph that, you're going to have, you can graph a position time graph for a turn, which is what we just looked at. So the velocity time graph we've been looking at is for a turn, which means that you stopped and you turned around, right? So you can use those numbers, those values to help you determine like your upper and lower bounds for your scale for your graph. You're going to label your key positions, your time positions, and then you want to start thinking about the shape of things, okay? So we know that between 0 and 30 seconds, that was a constant velocity. We had a straight line there on our velocity time graph. So that means that on our position time graph, a constant velocity is also represented by a straight line. So this will be a straight line in the positive direction, which means it'll angle upward. And then between 30 and 60 seconds, you had a deceleration. You were slowing down, which from the position time graphs we talked about last class, you know that if something is accelerating or decelerating, you're going to have a curved line. So here we would have a parabola. It's going to open down, And then you are looking at 60 to 90 seconds. Again, acceleration is still in a negative direction, so your parabola is still opening down. And then at the very last section, you have a constant velocity again. So you're gonna have another straight line. So it would look like this. So this is supposed to be meters east, but I got messed up. So you started at 0. You had a constant velocity from 0 to 30 seconds. We knew that the position we calculated right in here was about 600. And then we had another 300 meters that we traveled. We knew that this was going to be accelerating, so that's why this graph is curved right here. So at 60 seconds, we've traveled a total of 900 meters. And in this portion, we were slowing down. So we came to a brief stop at the top, and then we continued on in the opposite direction. Okay, so position is coming back towards 0, which means we've turned around. We are speeding up now, but we're going in the opposite direction. So we still have a curve because this is showing acceleration. So after you are speeding up, and if you're looking at the graphs, maybe on your slides, this is the portion of the graph where we went beneath the X line. So now we are speeding back up. We've gone another 300 meters. And then the last portion, this is the A4 portion, where we went 1,400 meters, but we went all the way back past our 0 point and extended ourselves and kept moving in the west direction. So for our position time graph, this is saying that you were accelerating with a constant speed, you slowed down, you stopped, you turned around, you sped back up, and then you kept on running and past your starting point. Okay, so just some key terms here with your velocity and time graph. Just remember that your area between the graph and the time axis is going to give you your position or your displacement. And then we are adding the new formulas of area. So area of a square or a box is going to be length times width, and then area of a triangle is 1/2 base times height. Okay, we have talked about this already. So if we have a line with a positive slope, velocity is increasing. The object is accelerating in the positive direction. And then if we cross the x-axis, it means that it has changed directions. So the opposite is also true of a negative slope. So the very last thing we're going to talk about, just really quickly here, because I have a class coming in, is comparing graphs. So this will be part of your homework assignment, is looking at what a position time graph and a velocity time graph look like, showing the same information. Okay, so we know that in a position time graph, if you're stopped, you're going to have a flat line at whatever position you were at. The velocity time graph would have you at 0, also a flat line though. If you have a constant velocity, so you're speeding up, your position time graph, or sorry, you're not speeding up, you're running, moving at a constant speed. So your position time graph would show that you're changing your position in a positive or negative manner with a tilt, and then your velocity time graph would give you a straight line. Speeding up here, position time graphs would give you a curved line to show acceleration. Velocity time graphs are going to give you a linear value there. So I apologize for having to speed through here because the bell just rang, but please read back through these slides, work on your assignments, and if you guys do have any questions, please let me know.